You know, people ask me all the time, why can I see through glass? And they think they know the answer. They say, well, glass is transparent. The atoms are arranged in a way that lets light pass through. It's got spaces between the atoms. The light just goes right through those spaces like a bullet through a fence. But that's completely wrong. Completely wrong. And the actual reason, the real reason you can see through glass is so much stranger and more wonderful than that simple picture that I want to tell you about it today. First thing you have to understand is that light doesn't go through glass. Not the way you think. It doesn't thread its way between atoms like a car driving down a street. That's not what happens at all. What actually happens is that the light, the electromagnetic wave, hits the first layer of atoms in the glass, and those atoms absorb that light. They take it in completely. The light is gone, destroyed. Then those atoms, because they've been shaken by that electromagnetic field, they start to oscillate. They wiggle. And when a charged particle wiggles, when an electron moves back and forth, it radiates a new electromagnetic wave. It makes a new light wave. And that new light wave travels a tiny bit further and hits another layer of atoms, which absorb it, get shaken up, and radiate yet another new wave. And this happens over and over and over, billions and billions of times, as you go through even a thin piece of glass. So the light that comes out the other side, that's not the same light that went in. It's a completely new wave generated by the collective behavior of all those atoms oscillating together in just the right way. That's what transmission is. It's this incredible choreography of absorption and re-emission happening faster than you can possibly imagine. Now, why does this happen in glass but not in a piece of wood or a brick wall? Well, that's where it gets interesting. In glass, the electrons, the charged particles that do the wiggling, they're bound to their atoms in a particular way. When light comes in, it shakes those electrons, but the frequency of visible light, the color of light we see, it doesn't match any of the natural resonant frequencies of those electrons in glass. It's like trying to push a kid on a swing at the wrong rhythm. You can still push them, they'll move a little, but they won't swing high. The electrons in glass oscillate just enough to re-radiate the light, but they don't absorb the energy permanently. They don't keep it, so the light keeps going, getting passed along from atom to atom. But in wood, in metal, in your skin, the electrons have different binding energies. They have resonances that do match visible light, or they have free electrons that can slosh around and absorb the energy completely, turning it into heat or other forms of energy instead of re-radiating it coherently. So the light gets scrambled, gets absorbed, gets turned into random motion, into heat, and it doesn't come out the other side as light anymore. That's why wood is opaque. Now here's where it gets even weirder. You might think, okay, if each atom absorbs the light and then re-emits it, the re-emitted light could go in any direction, right? I mean, if I shake an electron, it's going to radiate in all directions like a little antenna. So why doesn't the light scatter everywhere? Why does it keep going straight through the glass? Why doesn't glass glow in all directions when you shine light through it? And the answer is quantum mechanics. It's interference. See, each atom, when it re-radiates, it does send out waves in every direction, little spherical waves spreading out from each atom. But here's the thing. There are so many atoms, unimaginably many atoms, in even a tiny volume of glass, and they're all oscillating together in phase because they were all driven by the same incoming wave. All those little spherical waves they emit, they interfere with each other. In most directions, the waves from different atoms arrive out of phase. One wave is going up while another is going down. They cancel. They destroy each other. The interference is destructive. But in the forward direction, in the direction the original light was going, all those little waves add up. They arrive in phase. Crest meets crest. Trough meets trough. They interfere constructively. And that constructive interference recreates a single, strong wave moving forward, moving in the same direction as the original light. That's why the light keeps going straight. It's not because each photon is flying through empty space between atoms. It's because of the quantum mechanical addition of all these probability amplitudes from every possible path the light could take through the material, and almost all of them cancel out except the forward direction. This is the same kind of thinking I used when I developed the path integral formulation of quantum mechanics. You add up contributions from every possible path, every possible way something could happen, and you weight them by their quantum mechanical phase. Most of them interfere destructively and disappear. Only certain paths, the classical paths usually, survive the interference and give you the behavior you observe. In glass, it's the forward path that survives. And there's more. The speed of light in glass, The fact that light slows down when it goes through glass, that's also part of this story. See, the light isn't really slowing down in the sense that each photon is moving slower. Photons always move at the speed of light, see, the cosmic speed limit. But what happens is that the process of absorption and re-emission, it takes time. A tiny, tiny amount of time, but it's not instantaneous. Each atom absorbs the wave, its electrons oscillate for a moment, and then it re-emits. And because this happens over and over, the wave that propagates through the material, the collective wave from all those atoms, it appears to move slower than c. The effective speed, the phase velocity, is less than c. That's the refractive index. It's a measure of how much this delay adds up. And different frequencies of light, different colors, they interact slightly differently with the electrons in glass. Blue light, higher frequency, it shakes the electrons a bit differently than red light does. The delay is different, so blue light and red light travel through glass at slightly different speeds. That's dispersion. That's why a prism splits white light into a rainbow. Each color bends by a different amount because each color has a different speed in the glass. And when light changes speed at an angle, it bends. That's refraction. But let's go back to this idea that light is getting absorbed and re-emitted. Some people hear that and they say, wait a minute, doesn't that mean there should be a delay? If I turn on a flashlight on one side of a window, shouldn't there be a tiny pause before the light comes out the other side while all this absorbing and re-emitting is happening? And yes, there is a delay. There absolutely is. But it's incredibly short. Light moves fast. Even in glass, even slowed down to, say, 2/3 the speed of light in vacuum, it still crosses a pane of glass in a billionth of a second or so. You would never notice. Your eye, your brain, the electronics in any detector, they're way too slow to see that delay. It's real, but it's imperceptible. Now, I want to talk about what happens at the surfaces, because that's where things get really interesting. When light hits the surface of glass coming from air, some of it reflects back and some of it goes into the glass. Why? Well, at the boundary, the electromagnetic field has to be continuous. The wave on one side has to match up smoothly with the wave on the other side. But the wave in air and the wave in glass, they're traveling at different speeds because glass has a different refractive index. To make everything match up, to satisfy Maxwell's equations at that boundary, you have to have a reflected wave going back and a transmitted wave going forward. It's not a choice, it's a requirement of the mathematics. And the amount that reflects versus the amount that transmits, that depends on the difference in refractive indices. If the indices are very different, like air to glass, you get maybe 4% reflection at each surface. If they're similar, you get less. If they're exactly the same, you get no reflection at all. The wave just keeps going as if there was no boundary. This is why you can make anti-reflection coatings. You put a very thin layer of some material on the glass, a material with a refractive index halfway between air and glass, and you make the layer just the right thickness, a quarter of the wavelength of the light you want to transmit, then the light reflected from the top surface of the coating and the light reflected from the bottom surface of the coating, where it meets the glass, they travel slightly different distances. And if you get the thickness just right, those two reflected waves are exactly out of phase. They interfere destructively. They cancel each other out. No reflection. All the light goes through. That's how you make camera lenses and eyeglasses that don't glare. It's all interference. And here's something people find very hard to believe. When light goes from air into glass, into a denser medium, it bends toward the normal, toward the perpendicular to the surface. When it goes from glass back into air, it bends away from the normal. And if you hit the boundary at a steep enough angle, from the glass side, the light doesn't come out at all. It all reflects back. Total internal reflection. This is how fiber optic cables work. Light bounces down the inside of a glass fiber, hitting the walls at such a steep angle that it never escapes. It just keeps reflecting, traveling miles and miles without significant loss. And that's how we send information, phone calls, internet data, at the speed of light through tiny glass threads. But why does light bend at all? Why does refraction happen? And again, it comes back to this idea of the wave interacting with the material. Imagine a line of soldiers marching across a field, and they hit a patch of mud at an angle. The soldiers on one side of the line hit the mud first and slow down while the others are still on firm ground. The line pivots. It bends. The direction of the whole group changes. That's refraction. The wave front of the light, the crest of the wave, it hits the glass at an angle. Part of it slows down while part of it is still in air. The wave front tilts. The direction changes. Feynman had this beautiful way of explaining it using the principle of least time. Light, he said, takes the path that requires the least time, not the shortest distance, the least time. If light is going from point A in air to point B in glass, and it's faster in air than in glass, then the path that takes the least time is not a straight line. It's a bent path, one that spends more distance in the faster medium, air, and less in the slower medium, glass, but still gets to point B. And if you work out the geometry, if you calculate which path actually minimizes the travel time, you get exactly Snell's law, the law of refraction. The angles and the speeds and the refractive indices all match up perfectly. Nature is lazy. Light takes the quickest route. But, and this is crucial, that's not really how it works in quantum mechanics. That's a classical approximation. In quantum mechanics, light doesn't take one path. It takes all paths, every possible path from A to B. Paths that bend more, paths that bend less, paths that loop around, crazy paths. And each path contributes a little quantum amplitude, a little arrow in the complex plane, and you add them all up. Most of them cancel out because their phases are random, but near the path of least time, near the classical path, the phases of nearby paths are almost the same. They don't cancel, they add up. That's why light appears to take the path of least time. It's not that it chooses that path, it's that all the other paths interfere away and the least time path is what survives. This whole picture, this way of thinking about light and matter interacting, it applies to everything, not just glass. Metals, for instance, they're shiny because they have free electrons, electrons that aren't bound to any particular atom. Those free electrons slosh around very easily when light hits them, and they re-radiate very efficiently. But they radiate in such a way that the light doesn't penetrate. It reflects. Almost all of it reflects. That's why metals are opaque and shiny. The free electrons are like a mirror at every layer. Water is transparent for the same reason glass is. The binding energies of the electrons in water molecules, they don't match visible light. But water absorbs infrared, longer wavelengths, because those frequencies do match vibrational modes of the molecules. That's why microwaves heat water. They're tuned to a frequency that water absorbs very well. And if you go to very high frequencies like X-rays or gamma rays, even glass becomes transparent in a different way. The photons are so energetic that they don't interact much with the electrons at all. They just blast through. That's why you can take an X-ray picture through your body. The X-rays mostly ignore the atoms and go straight through, except where they hit something very dense like bone, where there are more electrons to scatter them. Now there's one more thing I want to tell you about, and it's perhaps the strangest part of this whole business. Glass is not a crystal. It's not a regular ordered arrangement of atoms like you have in a salt crystal or a diamond. Glass is what we call an amorphous solid. The atoms are frozen in place. They're not flowing like a liquid, but they're also not arranged in a neat repeating pattern. They're jumbled, disordered, like a snapshot of a liquid that suddenly stopped moving. And this makes glass very weird. Is it a solid or is it a very, very slow-moving liquid? There's an old myth that says glass flows over time, that old windows are thicker at the bottom because the glass has slowly dripped down over centuries. That's not true. Old windows are thicker at the bottom because that's how they were made, and because glaziers often installed them with the thick side down for stability. But the question of what glass really is, that's still debated. At room temperature, glass is solid. The atoms don't move, but there's no sharp transition, no sudden freezing point where it becomes a true solid. It just gets more and more viscous as it cools until it's effectively frozen. And yet, despite this disorder, despite the lack of a crystal structure, glass is transparent. The atoms are jumbled, but they're still close enough together, still uniform enough on average, that the interference picture I described still works. The re-radiated waves still add up in the forward direction. The disorder doesn't scatter the light in random directions, at least not much. That's remarkable. It tells you that the transparency of glass is not about having a perfect crystal. It's about having the right kind of disorder, the right density, the right electronic properties. So, when you look through a window, when you see the world outside, you're not seeing through empty space between atoms. You're seeing the result of an unimaginably complex quantum mechanical dance. Every atom in that glass is absorbing and re-emitting light, shaking in response to the electromagnetic field, contributing its little piece to the outgoing wave. And all those contributions from billions of atoms, they add up in just the right way. They interfere in just the right pattern to recreate the image of whatever is on the other side. The light doesn't go through. It gets passed along, atom by atom, wave by wave, until it emerges on your side, carrying the information about what's out there. That's what transmission is. That's why glass is transparent. And it's not simple. It's not obvious. It's one of the most beautiful examples of quantum mechanics and electromagnetism working together to create something we take for granted every single day. Glass is weird. Matter is weird. Light is weird. And the fact that we can understand it, that we can write down the equations and predict exactly what will happen, that we can engineer materials with the properties we want, that's what physics is all about. It's about looking at the world, at the ordinary things like windows and mirrors and prisms, and asking why. Why does it work that way? And then digging deeper and deeper until you find the real answer, the strange and wonderful truth that nature has been hiding in plain sight all along.